Yeah, so obviously I had planned on Wednesday to go through most of what you needed for the homework. And then spend the next few days like working on that. That didn't happen.
Plans and Mother Nature's
So
like,
we'll
nope.
see where we are. Sorry?
You make plans and then the weather's like, never mind.
Yeah.
It snowed. No, it snows like one thing.
I'd say the rain too.
I would try to make
Like what this?
Yeah, no, it's just the weather type.
I'm in Portland, but it's not fall.
That's what it is. Snow shut down Portland.
Portland, I'm just there.
Some people driving around in the middle of it last week were like, oh, this isn't as bad as last month. I'm like, are you kidding me?
Yeah, wait, what?
So the real question is, where were we?
That is awesome.
I almost feel like just starting over again.
Or which class is this?
Be 215. Restart.
This is 215.
There it is.
Yeah.
So, let me talk about rules of inference. Harper murder. He was dead anyway. And we'll talk about this, and then we'll take a look at the homework and see where we stand with that. And a lot of the homework, the stuff related to proving certain things, is talking about rules of inference, which we hadn't gone through yet. So let's talk about this, and we'll take a look at the homework, and if we have to push it back, we will. And the next homework, which is due on Monday, I don't think that'll happen, but we'll figure it out.
Yeah, I got questions like what is like the difference between implied and implied? That's my question.
So, when we say A implies B, that means if A, then B. So A arrow B. If this is the case, we can say B is implied by A. It's just a different form of that.
It's kind of like it.
So A implies B, B is implied by A. All of that means basically if A is true, then we can prove that B is true also.
So we would ask, like, give an example other than X that implies X. Would you just make something up through the truth table, or would you just write a blanket proposition statement?
So what exactly does it ask?
So you have, it gives you a proposition that you have to do a truth table for, then it asks for something other than X that is equivalent to X, and then the following part is to give an example other than X that implies X.
Okay, so what is X in this example?
It's open paren, P and not Q, close paren, or open paren, R and P, close paren.
So that's the proposition X. Okay. So first part gives something.
It's make the truth table for that.
Okay,
And
second
then the
part.
second part is give an example other than X itself, equivalent to X.
So something equivalent to X. So basically rework this into a different expression.
So you could say like P and.
Yeah, you could use
P or
distribution
R.
here.
And then what about give an example other than X that implies X?
Okay, so find find a y that implies x. So we're looking for something that if it is true, this will also be true. Clearly, if P and not Q or R and P is true, then this is true. Okay, so that's basically x implies x. So they're looking for something else that if it's true, will imply this. So if you find an equivalent expression to this, right, something that's logically equivalent, that would certainly imply x. There may be other things as well. So for example, suppose x is the proposition, P and Q or P. Well, if you look at this, this is not logically equivalent to just the expression P, right? These are different expressions from each other. But if P itself is true, then we know that X is true. Because if P is true, then this part is true, and so the entire OR is true. So P itself would be an example of a proposition that implies X, even though P and X are not the same statement. So that's the idea that it's after in there. So play around with it and see if you can find something other than X itself that you can absolutely say, if that something is true, this is also going to be true. Make sense? Okay. Yeah.
So we can take one of those OR like variables like R and P. So if R and P is true, then the whole X is true.
Sure. All right. Other questions, since we're doing questions? Okay, rules of inference. If it is sunny, then I'll go for a run. There's a proposition. It is sunny. That's another proposition. Therefore, I'll go for a run. I'll go for a run in the third proposition. This horizontal line means therefore, basically. Okay, here's the thing. We don't know if this proposition is true or false, nor do we know if this or this proposition are true or false. But what we know is that if this is true and this is true, then this is true. Two slightly different things. The first thing is saying, is this true, is this true, is this true? We're not making any claims about those one way or another. What we are claiming is that if this is true and if this is also true, then this must be true. In other words, we can infer this proposition from the truth of these propositions. So if we label these things, let P be the proposition that if it's sunny, I'll go for a run. Let P be the proposition that it's sunny. Let me change this. Put this over here. Let P be the proposition be it is sunny. And let Q be the proposition I'll go for a run. All right, so we can rewrite these propositions in terms of P and Q. If it's sunny, then I'll go for a run. That says if P, then Q. It is sunny is simply the proposition P. Our conclusion is simply the proposition Q. All right, this is a rule of inference. It says if P implies Q and if P is also true, then Q is also true. And we could write this a little more awkwardly. Like that. But that just looks like gobbledygook. It just looks like a bunch of P's and Q's and logical symbols. This lays out things a little more logically. We're starting with this, and we're concluding Q. And sometimes when you see it in this form, you see that double arrow that shows up in the book. And it's saying that this left side infers this right side. So this is a rule of inference called modus ponens. If you don't like the fancy Latin word, the book calls this detachment. So if we're given if P then Q and P, we can conclude Q simply by saying modus ponens, or detachment. Now we could also do this with a truth table. So our truth table for the conditional is true in all cases except this one. Hypothesis is true, conclusion is false, then the implication is false. Otherwise it's true. And so we would say if P then Q and P, and this is going to be and so if we construct the truth table column for this implies Q, this is true, this is true, this is true, and this is true. Right, the only time that this would be false is if this is true and Q turns out to be false, and that never happens. So in all cases, this implies this. But that's just truth table manipulation. That, to me, is kind of devoid of deeper meaning. This is, to me, much more logical, right? If P, then Q, and I'm telling you that P is true, well, if P is true, then Q must be true. That's all it's saying. So if you come to class, you'll pass the exam. You come to class, therefore you pass the exam. But here's what we can do with rules of inference. Suppose we're given these 26 statements. If A, then B. If B, then C. If C, then D, and so on. If Y, then Z. And we're also told that A is true. I claim, therefore, Z is true. And this makes sense logically, right? If it's Monday, I've got to get up early. If I get up early, I'm going to have breakfast. If I have breakfast, I'm going to make orange juice. If I make orange juice, I'll have to turn on the electricity. If I turn on the electricity, my feet will get wet. And it's Monday, therefore my feet are going to get wet. There's a fuse box outside or whatever. Right? So logically that makes sense. And we can prove this using this idea of rules of inference as follows. We can say if A then B, that's given. We call it a premise. It's something that we're given. And we're also told that A is true, that's a premise. And therefore, we can conclude B. That's modus ponens. And we're told that if B is true, then C, that's a premise. Therefore, we can conclude C, that's again modus ponens. And we can keep doing this. And it's going to take a little over 50 steps to get to Z. If you try to do this with a truth table, you're going to have 25, 26 columns, but how many rows are you going to have? You're going to have 2 to the 26th rows for all possible combinations of A through Z, true or false. That's not a good way to try to prove this. It'll work, but it's a lot of legwork. And this is somehow sort of going after the logic of why this is true. Whereas the truth table approach is just kind of blindly plugging in possibilities. And so that's why rules of inference are nice sometimes. And so there's some homework questions that ask you to show things using truth tables, and there's some that will ask you to do it using logical reasoning. When we say logical reasoning, we're talking about doing something like this. Like that. So let me offer you some other rules of inference. Bless you. And these are in the text on page 59. So modus ponens is one of our key ones, detachment. Modus tollens is indirect reasoning. If P, then Q. If we're given that, and if we're also given not Q, we can conclude not P. This is indirect reasoning. And that should make logical sense too. If it's sunny, then I'll go for a run. I did not go for a run, therefore it cannot be sunny. Because if P were true, we know that Q would have to also be true, and we've been told Q is not true. So P cannot be true. It's just proof by contradiction, basically. So indirect reasoning. So those are the two sort of super interesting ones. And then we got some miscellaneous ones. If we know that P is true, then we know that P or Q is true. Doesn't matter what Q is. Because for P or Q to be true, we only need one of these to be true, and we've just been told that P is true. So that's disjunctive addition. If P and Q is true, then P is true. Because we just said both P and Q are true. So clearly P has to be true. And similarly, Q has to be true. That's conjunctive simplification. And let me mention one more. This is just a chain rule. If P implies Q and Q implies R, then P implies R. And that hopefully makes logical sense also. All right, along with rules of inference, we have what are called fallacies. So here's two things that look like rules of inference but aren't actually logically correct. Given if P then Q, and given Q, you may try to conclude P. That's not logically true, that's a fallacy. That's called the fallacy of affirming the conclusion. If it's Friday, then we're in CSE 215. That's a true statement. If it's Friday, we're in CSE 215. We are in CSE 215, therefore it must be Friday. It does not follow logically. Okay, it's a fallacy. So don't use this when you're trying to construct. And this fallacy is called the fallacy of affirming the conclusion. Basically, we have a conditional statement. We say the conclusion is true, and then we try to argue that the hypothesis is true. And that's a fallacy. Our other fallacy is similar. This is the fallacy of denying the hypothesis. If it's Friday, then we're in CSE 215. It's not Friday, therefore we're not in CSE 215. Doesn't follow. So here we have a conditional statement. We deny the hypothesis. We claim the hypothesis is false, and we're led to a false conclusion. So those are the two key fallacies to watch out for. Affirming the conclusion and denying the hypothesis. So let's talk about proofs. So a theorem is a statement that can be shown to be true. And a proof is a way of showing that a statement is true. So, methods of proof. And there's two main classes of proofs we're going to work with, direct proofs and indirect proofs. Roughly speaking, a direct proof starts with what we know, keeps using rules of inference to conclude more and more things that we know, and eventually gets to the thing that we're trying to prove. An indirect proof kind of goes in the opposite direction. We're trying to prove this. Okay, suppose this is not true. And we use rules of inference to conclude more and more things until we reach a contradiction. And then we say, okay, so this original thing, if it's not true, we have a contradiction. So this original thing must have been true. It's kind of like a direct proof with a contrapositor. So we'll see examples of these briefly. Let me use the following definitions. An integer n is even if n equals 2 times k for some integer k. Does that make sense to people? When we say a number is even, it just means it's 2 times some integer. So 100 is even because it's 2 times 50. Negative 12 is even because it's 2 times negative 6. Negative 6 is an integer. 7 is not even because it's 2 times 3.5, and 3.5 is not an integer. And there's no integer we can multiply by 2 to get 7. So an integer n is odd if n equals 2k plus 1 for some integer k. So 7 is 2 times 3 plus 1. So 7 is odd. And you can probably convince yourself that every number is either even or odd, and no number is both. Right? 0 is even because it's 2 times 0. 0 is an integer. So 0 is even, 1 is odd because it's 2 times 0 plus 1. And we go from there. So these are definitions. And we'll use those throughout. So here's a theorem. If n is even, then n squared is also even. Four is even, 4 squared is 16, that's also even. Negative 6 is even, negative 6 squared is 36, that's also even. Seems to work. So how do we prove this? We want like a airtight, valid in a court of law kind of argument here. So it's got to be more than seems to work. So how do you go about a proof like this? Well, think about your definitions. N is 2 times some number. We're claiming n squared is also 2 times some number. So why is 6 even? Well, because it's 2 times 3. Why is 6 squared even? Because it's 2 times 18.
Because an even number plus another even number is even.
This is true. Do we know that?
Prove that too.
Let's prove it. b are even, then a plus b is even. And that seems to work if you try a few numbers. So mathematically, if a is 2 times some integer and b is also 2 times some integer, can we show that a plus b is 2 times some integer? Sounds like algebra. So let's do that. So proof. So I'm going to number my steps. I'm going to say step 1. And step 1, I'm going to say A is even. And why can I say that? I don't know if A is even. I'm just assuming it. It's a premise. A could be the oddest number in the world. But I'm assuming A is even, because if A is odd, I don't have to show that A plus B is even. So I'm assuming A is even. That's a premise. Step 2, I'm going to assume that B is even. That's also a premise. Well, I can't do algebra on the word E-V-E-N. I gotta have symbols and numbers and stuff. So I'm going to use my definition of an even number and say A equals 2 times K for some integer K. And that's the definition of A being even. All right, this next step is potentially slightly tricky. What can I say about B? We know it's even. And we know an even number is 2 times K for some integer K. But you gotta be careful here, because if I write B equals 2 times K, I just forced A and B to be equal to each other. Okay? And that will trip us up eventually. This K here is just a placeholder. There's nothing magic about K. I could have said it's even if it's 2 times W for some integer W. It's just a placeholder, but since I'm using K to represent 1/2 of A, I don't want to use K here. So B equals 2 times J for some integer J. And that's a definition of even. So be careful of that. Okay, I'll circle that in red. And if we call them both K, it's not really going to change our result, but in some cases, it could. So now we've written a statement that's true for any even number B, not just for a B that happens to equal A. All right, well, what should we do next? So far, all we've done is premises and definitions. We'll do some algebra somewhere.
A plus B is equal to K plus 2J.
Yeah, let's add A and B, because we're trying to make some statement about A plus B. So A plus B equals 2K plus 2J, and that's algebra. And now we're really close to what we're after. We want to show that A plus B is 2 times some integer, so let's just factor out. That's more algebra. So A plus B is 2 times K plus J. If you want to be really formal, you could state at this point that K plus J is an integer. Since K and J are integers and adding integers give you integers, but we'll take that as understood for now and simply jump to step 7. A plus B is even, and that's the definition of even. If it's not absolutely clear to a distracted reader that this is an integer, put in another statement there and say explicitly K plus J is an integer. and make sure that makes sense. If this is something like k plus j over 3, we don't know that that's an integer unless we know something about j. Yeah?
So is this direct proof?
This is a direct proof. We're stating things that we know, and we're working forward, and hey, bang, look what popped out down here, the thing that we wanted to prove. That's a direct proof.
Do we need to refer back at all to the line numbers before? In the textbook it had like,
Yeah, if it makes sense to.
That makes no big deal.
It's pretty straightforward here, everything is just coming from the previous, but yeah, if you're combining things like chain rule on steps 1 and 3, you can mention that. All right, so let's prove that if n is even, then n squared is even. So step 1, n is even. That's a premise. Step 2, n equals 2 times k for some k, some integer k. That's a definition of even. What's a good step after this?
Isn't multiplication repetitive addition?
It is. We don't have to go that route though. We can actually trust our multiplication. But yes, since n's an integer, we n squared would be n plus itself n times.
like I said, n times n is equal to 2k times 2k.
And what's 2k times 2k? 4k squared. Is 4k squared even? It sounds even. How can we?
2 times 2k squared.
Yeah, this is actually equal to 2 times 2k squared. That's all algebra. And so we've taken n squared and we've written it as 2 times something, and since k is an integer, 2k squared is an integer. So we can say n squared is even. That's a definition of even. So that's another direct proof. We started with what we knew, we applied rules of inference and definitions, and suddenly we got a conclusion that was exactly what we were trying to prove. All right, let's look at an indirect case. Let's prove that if n squared is odd, then n is odd. So I've got a number in my mind and I tell you its square is 81. 81 is odd, you can conclude immediately the number I'm thinking of is odd. That's what this theorem says. We'd like to prove it. And it's tempting to say if we have an odd number, then its square is going to be odd, and that's pretty easy to show, but that's a totally different statement. We can show that if n is odd, it's got the form 2k plus 1, and 2k plus 1 squared is 4k squared plus 4k plus 1, which is 2 times something plus 1. So we can show that if this is true, this is true. But that does not prove that if this is true, this is true. Right? That's like saying if n equals 11, then n is odd. That's totally different from saying if n is odd, then n must equal 11. Okay, you can't prove things in the opposite direction. You got to say, given this, can we prove this? So what can we say? N squared is odd. That's a premise. And so we can say n squared equals 2 times k plus 1 for some integer k. That's a definition of odd. But how do we get from that to somehow showing that n itself is 2 times some integer plus 1? And it's not clear really where to go from here. We could take the square root of both sides, but what's the square root of 2 times an integer plus 1? That gets us into a whole quagmire that we're not going to come out of. So it's not clear where to go from here. So a direct proof of this is not immediate, but an indirect proof is very easy. So this is a direct. Let's look at an indirect proof. Suppose n is not odd. Okay, this is our assumption, our hypothesis. Well, then we know that n is even, because if you're not odd, you got to be even. So that's just definition. If n is even, we know that n squared is even because we just proved that. So n squared is even. So that's an earlier proof. And if n squared is even, then n squared is not odd. That's a definition. So what we've proven is that if n is not odd, n squared cannot be odd. Since we're told that n squared is odd, n itself must have been odd. So let me put in this first step here. So we start off with n squared is odd. That's our premise. All right, and then we suppose n is not odd. And we get down to the conclusion that n squared is not odd, which is a contradiction of our premise. So this is the only thing that we assumed, and by assuming this, we got to a fallacy. On the basis of that, we can conclude that this assumption must be false. And so from all of this, we conclude, therefore, n must be odd. So what did we actually do? P is the proposition that n squared is odd. Q is the proposition that n is odd. What we did was we showed that if n is not odd, then n squared is not odd. The contrapositive of this is if P, then Q. So we basically did a direct proof of the contrapositive. That's really what an indirect proof is. That make sense? So these take a lot of practice, and the more you practice with them, the more they'll gel. All right, let me take a look at the homework. So, well, ask me questions about the homework. Which ones aren't clear? Because I don't have the numbers written down. Yeah. Sure.
So, because n squared is not odd, and that doesn't work with the premise, so it is going to be odd, that's it.
So if we assume that n squared is odd and we make this assumption, we're forced into a contradiction, which means this assumption was incorrect. So we can conclude from that that this is false, which means that n is even. But the other way to think about this is really just start with this, conclude this, and so we've shown not Q implies not P, and then invoke the contrapositive and say therefore P implies Q.
We look at chapter 3.5, 6, number 6.
Determine the validity of the following argument. That one? Okay. Well, let me do something similar. Let me look at number 5, so I don't take away the fun of your homework question. Let's look at 5B. If the races are fixed, or the casinos are crooked, then tourism declines. So that's the statement we're given. If tourism declines, then something like the police will be happy. The police are never happy. Therefore, the races are not fixed. So we want to prove this in 48 seconds. So make some propositional variables. So F can be the proposition that the races are fixed. C can be the proposition that casinos are crooked. T can be the proposition that tourism declines. P can be the proposition that police are happy. These are just defining some propositional variables. Now look at what our statements are telling us. If the races are fixed, so F, or the casinos are crooked, C, then tourism declines, T. So we translate the statements we're given into these propositional sentences. If tourism declines, then the police are happy. The police are never happy is not P, and we're trying to conclude the races are not fixed, so not F. So mathematically, what we're being asked to do is prove this theorem. So that's the first step, is take your statements, write some propositional variables. Second step, take this, translate it into the language of propositional calculus. Third step, try to prove this theorem, prove that this follows from these premises, using rules of inference. So F or C implies T, T implies P, not P. So we don't have time to do this, but I'll ask you to work on this at home, and we'll work through this in detail tomorrow. But start with these two, and use those first two rules of inference we talked about, and see what you can conclude from this and this. In particular, if T is true, then P, and we're told P is not true, that's going to force you to conclude that T is not true. And now you've got something else implies T and you got not T, that's gonna let you draw a conclusion about this. And work forward from there. Page 59, all the rules of inference. Page 58 are some of the properties of these operators. Mostly page 59, see if you can formally take these things and turn it into this thing. And we'll run through that tomorrow.